welcome to another episode of the Commonless Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Today, we're going to be talking about logic programming and specifically the programming language Prolog, a pretty revolutionary programming language that has been around for it's about 40 years now, I guess. It was created in the 19, oh no, actually even longer than that, in the 50s and sorry, 60s and 70s. So it's about 50 years old now. Um, it was created originally in France, in the University of France. Prolog originally stood for Programmation and Logic, and it was created as a way of essentially implementing and interpreting horn clauses, which, for those of you who know first order predicate logic, it's a way of actually defining what we would consider to be logical facts inside. It's actually a formula that can essentially be used to produce an answer of true or false. Um, Obviously, with Prolog, you can actually end up leveraging um, many um, many other ways of handling solving certain types of queries and stuff. But at its heart, it's nothing more than the ability to take a bunch of constraints and facts and be able to resolve these logical clauses, these horn clauses, in a procedural manner. Today, we're going to be focusing on a bit of history, mainly because, I think it's important for folks to understand some of the logic programming history of Prolog. And in the book, we're going to be covering specifically two aspects of Prolog of the four that Dr. Norvig actually mentions in terms of what actually of the three that Dr. Norvig mentions as being the advantages of using Prolog as a way of designing artificial intelligence systems. All right. I will say that as a side note, and this is something that's separate from what the book actually is, I believe that Prolog was used to actually even design some additional or later query languages. Um, Most popular of them is being Datalog, which allows you to do what are called recursive queries on top of databases. This is associated with one of the particular pieces that or reasons that Dr. Norwood brought up about learning Prolog and logic programming in general, but I wanted to at least give some of that information out there before we get started. If you like and subscribe, like our content, please hit the bell icon, hit the subscribe button, so that you can enjoy further um, Atlanta functional programming content. We are a programming language meetup in Atlanta, Georgia. Our main goal is to promote the use of functional programming as a complementary paradigm, if not a, a primary paradigm for doing software application development in large-scale systems. We do welcome talks on many topics outside of functional programming, as well as and its uses and its roles. But our main focus is functional programming. We are the home of the Common Lisp Study Group, as well as many other study groups. For those of you who are interested in giving a talk on our platform, feel free to reach out to me. I am Bugram on Functional Programming Slack, as well as on the Lisp Discord server for those of you who are users of either of those platforms. Additionally, for those of you who are members of the Tech 404 community in Atlanta itself, I am also Bugram on Tech 404, so feel free to reach out to me there, provide your talk topics, and we can get you scheduled. Additionally, before I begin, I want to also mention that Atlanta Functional Programming is is looking out for a new home to do our in-person talks. For those of you who are uh, available or have ideas for new venues, feel free to reach out to me also in those avenues that I mentioned earlier, and I'll try and schedule new talks in person as well as other meetups too as well. But until then, um, all of you, we have been mainly a virtual meetup for the past years, and I will be announcing more additional virtual meetups as time progresses. Stay tuned to our meetup page if you are interested in hearing about our additional events, as well as stay tuned to the YouTube channel for some recording of those events once they arrive. So, as I mentioned, the story of Prolog actually begins in the 1960s, specifically in France. And here, specifically, Philip Roussel took over British logicians uh, Robert Kowalski's procedural interpretation of horn clauses, and looking at his logical framework, he was motivated to actually use this in logic programming in general as what they were calling at that time declarative knowledge representation languages, in order to essentially present what we consider to be facts and observations about the physical world in a way that can be queried and to answer some basic questions. Additionally, once they are in these horn clause forms, as we will see later, it made it easier for the actual interpreter, if not the Prolog program that you were trying to create, which, by the way, would end up ultimately being in the form of a query that you want the Prolog interpreter to go and solve by looking at the knowledge base of knowledge representation facts that were written as horn clauses in order to provide you an answer and give you, some sort of answer to to that query in terms of bindings and in what they call logic variables. Again, we'll touch base on what that means in uh, later. The one thing about this is it was very successful once it was designed in 1972, and it was originally written in France in Fortran before moving his way to University of Edinburgh, which actually ended up creating a different syntax called the Edinburgh syntax, which is what we're going to end up seeing, which is a variation of it that was written for Lisp. Um, and it's particularly important to understand that because if you see older programs, they may be written in a different way. Okay. Um, I'm sure there are probably Prolog programs now available that are still have the ability to actually go in and uh, you can actually run on modern interpretations of Edinburgh Prolog, like SWI Prolog. Second here. Now, one thing I wanted to bring up related to Prolog is the fact that there were many reasons for Prolog to actually exist, and additionally why it became popular. In fact, on the European side of the world, it was a very popular language for artificial intelligence. In fact, in the heyday of real big AI, before the recent renaissance thanks to machine learning and LLMs, on the European side, they were favoring Prolog for actually designing their logic programs and AI systems, whereas Americans were favoring the Lisp variants because of um, the ability to write declaratively in the syntax made it easier for them to at least design certain types of programs very in a very simple fashion compared to using common Lisp. Um, Obviously, Prolog has been extended with many features, mostly related to logic programming. In some cases, if you use newer versions of Prolog, many of which may or may not be added in the Prolog interpreter that we're going to be discussing in today's, well, as part of today's ongoing discussion and future discussions of Chapter 11. Um, there are features like negation has failure that's available. There's things in some Prolog variants that do what they call um, uh, constraint logic programming that have been that led their way into many implementations. And but for today's purposes, we may not be covering those. We will be covering only some of the basic reasons of using Prolog. And when we implement the Prolog interpreter, and when we talk about the Prolog interpreter that the book talks about, the actual implementation is of course available in its entirety on, I think, the Norvik's GitHub repo, which we'll be touching base in later talks. Um, it will provide you some ability to actually leverage a production level Prolog of the origin. I think it's close to the original Prolog that was implemented, minus a few features that may have been added as part of the extension languages, as I mentioned earlier. One thing I want to point out specifically is there the Prolog that we're kind of going to be discussing is, I'm almost certain to be sem almost completely declarative. At least from the examples I've seen, it look like they're declarative. I don't believe that we're going to be talking about things that I'm going to be mentioning right now, but modern Prolog and Prolog interpreters that are out there, they're not technically declarative in the strictest sense. There are constructs that allow you to write procedural programs, um, uh, it will allow you to read a Prolog program procedurally in order to understand certain types of constructs, like the one specific construct that comes into mind is something that's called the cut operator, which allows you to prune essentially. Um, it allows you to prune a particular subtree that you're trying to query, and cannot be backtracked. All right. And this is important when you're trying to do large scale um, Prolog queries, because Prolog's approach to actually doing a lot of search is um, DFS. Uh, and and so um, it's pretty important to recognize that these cuts allows you to, like, cut portions of the subtree that you're going to prune the actual tree of the query that you're actually trying to solve for the constraints. Okay. Um, Prolog, as I mentioned, has inspired many different variants, such as Datalog recursive, which allows you to do like recursive queries on a database. This data log is actually available for those of you who are using other logic programs, such as Clojure. I think has a data log variant inside of built into their standard library. Um, you could probably get a variant of that too as well in Common Lisp. I'm currently not unaware of a data log variant inside Common Lisp. But it also inspired the at least portions of Prolog inspired some aspects of Erlang, which many of you might know as being, some of the standard. It's pretty big. That's used in telecommunications, and it's used for writing large-scale concurrent programs too as well. But why are we talking about such a historic language in the context of artificial intelligence and in Common Lisp is probably um, uh, etching in many of your minds if assuming you haven't had a chance to read chapter 11 or have been following us along. Well, Prolog allows you to do, well, it incorporated specifically three things into the study of AI systems and in software engineering in general, right? Um, the first idea is using a uniform database. Okay, this is so the uniform database idea is not necessarily what we consider to be like a standard like relational database. What Prolog is talking about, and what I think Norvig was kind of alluding to, is there are representations of facts inside of this database, these observations, and um, you could use these databases particularly with a good compiler that could provide you efficient access to the facts inside of it, um, to actually do fairly complicated, very sophisticated queries to ask once you've structured the database and the data in such a way that allows these programs to be written. Okay. Um, Now, in this sense, because horn clauses themselves can be used to um, represent relations, right? Um, Prolog could be considered a Prolog knowledge base could be considered a type of um, relational um, database and relational programming language. Um, and and this is again based on the fact that we're using horn clauses, but Common Lisp in our implementation of Prolog inside Common Lisp will use a lot of the functional programming aspects of Common Lisp in order to actually implement some stuff inside Prolog. Um, One thing to note is the Prolog interpreter, when you're in the Prolog interpreter itself, you'll be writing relational queries. But the embeddedness of the DSL inside Common Lisp will make it so that those facts can be used as even higher order functions later on. Mainly like when you're doing unification or you're getting something out of it, if you're taking the query later on to actually be used as a named query, for example, that could also be a function inside of a higher order function. So this kind of seamless integration between functional and logic becomes natural thanks to the macro facilities inside of Common Lisp. And we'll see an example of that later on as we build aspects of this and once we've actually seen the actual Prolog interpreter that's available in Chapter 11. The additional thing that Prolog provides is something called the use of logic variables. All right. Now, these are very different than the variables that we've been talking about inside Common Lisp or any modern programming language, which is our settable pieces of information that you can assign later on. Think of it like bits of memory that could be reassigned in some cases. Although if you're using a functional variable, it will be immutable by default, and you would have to create a new one every time you try to mimic assignment, right? A logic variable, on the other hand, is something that is a variable whose value is bound when it's unified, all right? And unification is a specific term when it comes to logic programming, all right? Unification makes logic variables more like mathematical variables. They're not assigned, they're defined, they're not assigned. All right. There's a very different there's a different term here. You're saying you're defining a particular logic variable has this. Okay. So once that logic variable has been defined, it can never change. All right. Um, this is important because this makes Prolog programs more like queries that define a set of equations that constrain a particular problem and domain. Um, and it's unlike when you're writing procedural programs in Common Lisp. Okay, and we'll see an example of that when we touch base. Finally, like I mentioned, when we're talking about the search program, there's a big feature in most Prolog interpreters, and we will see this when we talk about this, and that is automatic backtracking. Um, what's nice about an automatic backtracking is um, you are searching through the relationals in the database to see if it particularly satisfies a query, but if you hit a dead end with automatic backtracking, it will um, go and do a depth first search in one particular portion of a tree, and if it hits a dead end, it'll backtrack and try all the other branches. So naturally, this will end up creating, in some cases, a potentially and for n facts in the database, if you have a particular n fact tree, for it to go through in the worst case scenario, if it's associated with the same fact, all n nodes. But Prolog has ways for you to allow you to prune different aspects of it. Like I said before, for example, with the cut operator, by defining queries with okay, if you hit a dead end here, cut it, and then let's move on. So this allows you to state Prolog programs has constraints to a particular problem domain, and um, and more specifically, you're stating constraints on the solution that Prolog should come up with. But you're not telling Prolog how to solve the actual problem or query that you're trying to do it. And it's particularly important to actually go in and uh, understand this difference. And it's an interesting way of looking at programs versus the way Lisp and most modern languages write programs. And for those who have probably encountered some of this kind of style in, say, Erlang or even Datalog, if you use Datalog or some other, you can understand its power because of the fact that you end up recognizing, well, we're actually defining a problem has a set of logical constraints, and we're having a solver, which is the Prolog interpreter, go in and figure out based on what it knows what variables are bound to what values, and it allows it to return it. Okay, I hope that makes sense to most people. Um, if you have any questions, obviously, feel free to ask away inside the chat. Um, but I will uh, move on to actually coming up with two things here. One is talking about uniform databases, and the other one is the basic unification idea. Are there questions with what we just discussed? All right, looks like there's nothing here. And okay, great. All right, so let's talk about facts first in our Prolog. Okay, so I'm going to show you examples of facts that you might see in Prolog, and then how it might look like. Well, not how it might look like, what it will look like in our Prolog. All right. So in a normal Prolog database, all right, you will have a fact written in the following way. Let's say that you're trying to write the population of San Francisco. All right. This is the example that was provided in the book. If you were using a Prolog interpreter, then this even will work with modern Prolog interpreters like SWI Prolog. If you could get Edinburgh Prolog, you can use that. There's also Guindian Prolog. SWI and Guindian are both, I think, available open source, so you can actually go in and leverage them. And they use the same Edinburgh syntax, so it will basically state the fact name, which is population. In this, we state San Francisco, although in this case we are going to shorten it to um, SF to be instead of writing the full name, and then we'll say 750,000. Okay. Obviously, that's not true anymore, but at the time that this book was written, I think is what this was. This is what the population was, kind of uh, written in. All right. Um, and we could also write, for example, say another piece of information about the state of California, saying that, capital Sacramento, CA. All right. So that means that Sacramento is the capital of California. All right. Please notice that there are periods in each of these. The reason why there are periods in each of these things is because the Prolog fact is a statement that needs to get inserted into the knowledge base. If you do not provide a period, um, my understanding is most Prolog interpreters will assume what you're trying to write is actually a horn clause, um, because you're trying to write it in um, multiple. It's like a um, logical and. All right, especially if you use a comma, it'll become a logical and. If you use a semicolon, it's a logical or. Um, and so, and think conjunction and disjunction for those of you who are students of first order logic. It's a disjunctive clause versus a conjunctive clause. Conjunctive being obviously the and disjunctive being being the or. The period essentially terminates the program and say, insert this into the knowledge base. Okay. The way our interpreter is going to look like is the following. So this is going to become, and I have to write it this way just because we haven't written our Prolog interpreter yet or our Prolog infrastructure yet. So you it'll be essentially a quoted system that's kind of like a quoted system, but obviously our Prolog interpreter would understand this, where the first argument of the S expression is going to be the fact name, and then obviously just like the rest of the arguments will be included as different types of variables. So in this first one, you'd have population of SF being 750, and then if you want to say capital Sacramento, California, and this is what it's going to look like inside of our actual thing. What's important about this is these facts, because currently the Prolog interpreter is not available. These facts has it. If I didn't quote them the way I did, they would end up being treated as S expressions, right? Strict S expressions where they think that the first argument is going to be the function call, right? So we have to actually go and figure out how to actually tell Common Lisp that no, this is a fact that we want to throw into quote unquote a database. Um, and so the Prolog interpreter that Norvig defined, it has the back arrow operator, which we will actually see in a moment. Okay, so it's going to look like this. Okay, I'm just going to comment this in right now, but eventually when we load the Prolog interpreter, you will see that this commented piece of code will allow us to insert, um, you know, uh, this fact into a database. So we have Alice likes Bob. Okay. There's many other ones that the book kind of like defined in terms of this, but I just kind of picked the most likely one that we would end up using. Um, this syntax though should bring up something important for most people. Again, we talked about the fact that in Common Lisp everything is since it's a functional language and an impure functional language, at that everything is you're defining a function, right? So likes is a function that could actually technically return um, uh, a list of say people that this person likes, right? Um, but if you want to access the reverse of this, the likers of a particular person, if we had this likes database, we would end up having to write another function to actually go and get the other relationship. The way Prolog is written, because we're dealing with the horn clause, we can actually have a single relation that's bidirectional effectively, right? We could get this likes who, and we could figure out who is bound to a particular person. But if we act likes who in a particular person, we can actually figure out who likes this particular person. So like in this case, if we asked the, and I'm just going to show you the syntax that we're ultimately going to be going for. If we ask, say, and let's say that this is already inserted to our database. If we asked this likes Alice question who, we'll end up getting essentially from our oh right, it's going to be a list of relations from our interpreter, a dotted pair with our quoted variable. Okay, and if we end up doing the opposite, okay, Bob, we look at Alice, and you'll see that, and there's different variations on this that you could write. You could say that, uh, and obviously one of these variations is going to be, let's say that you want to say who Alice. Can we get Bob again without reconstructing things? As far as I know, with this interpreter, you would have to write both directions if you want the unification to allow you to write general queries. Um, you can't write a single fact for it. But if you have the same structure, it will actually end up in a original program. It will only do a strict match on the relation as it stands. All right. There are The beauty of this particular this structure is that the same assignment structure, this back arrow, can be written in another way. All right. But the one thing to note is that question mark who. That question mark who is your logic variable. And we'll talk about it a little bit more when we talk about unification, but it's important to understand that that logic variable is what you are telling the program, the Prolog interpreter to solve. Okay, this is a very simple logic program. Naturally, given these logic variables and this ability to write these facts, we should be able to write inferential facts, meaning that these are contingent facts that the Prolog program itself can actually go and solve for you. And that is the second type of clause that this structure will give us, and that's called the rules. Okay, you may have heard Prolog rules before. This is basically what these rules will look like. Okay, in our Prolog program, we would end up writing, if we want to write a rule. Okay, this is an example of a rule. Um, we'd write the same insert here, and we would say likes, let's say Sandy question X if X likes cats. Okay, actually, sorry, if likes $X cats. All right. And what this basically says, Sandy likes anybody who likes cats. All right. And so if you look at this, the book talks about the the interesting notion of the notation that they're using. Um, I feel like it shouldn't necessarily matter if you actually look at it, but it's a usability thing that the reason why this arrow is written in the direction it is. Um, for those who understand that this is Common Lisp is a prefix language. If you wrote this infixed, and you're looking at it, it will end up becoming a logical assertion. If Sandy likes a person, that implies that that person likes cats. All right. You can also look at it as uh, a uh, a Prolog program as is, and this is basically what I was talking about in terms of the depth first search query that Prolog does. It's going to ask if you ever want to show Sandy likes somebody, all right, show that that person likes cats and Sandy will automatically like them. All right. That's a procedural interpretation of, or background chaining interpretation of the Prolog program, because you're reasoning backwards from the goal, which is Sandy likes a person, to the premise of that goal. And so uh, it's important to note that these kinds of rules, these backward chaining rules, are one way of writing rules into a Prolog database. Now, in the original implementation of Prolog, my understanding is backwards chaining and backtracking was the only availability. There was there are other things that are available in more modern Prolog variants, and even in what we call expert systems that end up being, we'll, I think, review some expert systems as part of learning Prolog later on in this chapter. And examples of them are like Myosin, which is an expert system for medicine. There was stuff for dealing with constraint satisfaction for engineering. I'm forgetting the name of it right now. Um, there was also TI World Explorer, which I believe was an expert system. A knowledge explorer was also available too as well. But all these expert systems, or even the most famous of them all, is Psych. Psych actually is an expert system that has a bunch of facts that were encoded in this way. These actually also incorporate a thing called forward chaining. So, starting with a premise and reasoning from its premise to a logical conclusion. Um, Prolog, as far as I know, like as we are implementing it, I think only implements backwards chaining. SWI Prolog, I think, has a way of doing forward chaining. At least last time I checked, I believe it did. So if you're looking at this book and you're trying to think, why is it saying that only backwards chaining is available? Because at the time that this was published, most Prolog, I don't believe, implemented forward chaining. All right. So we're only going to be dealing with backward chaining algorithms, and when we're dealing with Prolog, in at least in the context of this book and other projects, we may end up encountering uh, using forward chaining or having to look up how to implement forward chaining ourselves. All right. In the rule that you are looking at right now, you may see a general structure to what a rule constitutes. That is, the goal is the head of the rule, right? And that's in this case like Sandy X. All right. The body um are just the remaining, and you could think of this if you're thinking of Lisp functions, the rest arguments. Okay, all the rules that are this form will become the body of the actual rule that you're inserting. All right. So what does that mean? Well, that means that a rule that has, well, not a rule, a with this notation, a fact is just a rule with no body, right? So you can think of a fact is going to be always true, right? So it's always going to have to succeed. That's why if it has a rule with no body, that means it doesn't imply anything, all right? This will allow us to actually write complex rules in a single S expression form. Um, an example of that they provided is something that looks like this. And this is a complex rule that's going to consist of a conjunction essentially. So here, give me a second here, because obviously when I copy these for whatever reason, um, this is likely, oh, right, got it. This guy is that. Okay, this is likes up. Okay, and okay. So if you look at this complex rule, this is essentially if X likes Lee and X likes Kim, then Kim likes X. All right, and this rule provides, yeah, Kim likes anybody who likes both Lee and Kim. All right. One way to read this also is for any X deduce that Kim likes X, if it can be deduced that X likes Lee and likes Kim. All right. Um, so this is another way of interpreting this particular program. Um, but you could see how easy this structure can actually allow you to write fairly complex rules that end up getting resolved. But this is the idea of essentially using logic programming. So you write your rules, you write your your facts of the form as you see in line 22, and then your programs would end up being, okay, unify this particular query to this logic variable and tell me what values satisfy that query from this logic variable. And it could be multiple logic variables when we're dealing with um, unification. Okay, so I talked about unification quite a bit, but what is unification? All right. Um, the easiest way to define it, from what I understood from the book, is unification is nothing more than pattern matching. But in the case of pattern matching, which was a straight up lookup using a wildcard comparison, in unification, especially, it'll take two patterns, each of which that contain variables that are matched against each other. And so the difference between pattern matching and unification can be best deduced from, say, um, the following. In pattern matching, what it looks like in the structure, right? So in normal pattern matching, my understanding is if we remember from when we called PAIP match against XY, right? Sorry. And you saw 2 plus 1, okay? You know that in a pattern matching approach, we can actually go and return that x equals 2 and y equals 1 because we can actually determine from the pattern that x is 2 and y is 1 because of their positional arguments, right? And we don't even use the addition operator there. What that addition operator is there is like literally a placeholder. Any operator will end up being accounted for this particular thing. But with unification, unification extends this and generalizes a little bit in that if we end up changing this to a unify call, okay, and let me just delete this right now to give you the query results, okay, and instead of doing this, let's say that I'll give you the same answer for the book. Um, let's say that, yeah, that's right. So instead of deleting 2, let's delete 1. Let's say that this is x plus 1 and 2 plus question y. All right. In unification, it'll look at these two expressions and can deduce that x must be 2 and y must be 1. Okay. So 2, 1. Now, for those who are paying attention, um, you're noticing that I'm using dotted pairs instead of this straight up list. Well, that's because this is, when you create this, this is going to be a cons pair, okay? It's not part of a large list. And so the car and critter are going to be assigned directly when it comes to unification, okay? So this looks pretty simple. You might be thinking, um, that doesn't really tell me much about pattern matching and unification like being different. It just seems like we are kind of generalizing it within it. Well, this is slightly different because the pattern matching is just doing a straight lookup at the expression, whereas what unify is doing is it's taking the logic variables as you see in x and y. All right. We recognize that the logic variables can be um, um, just only assigned once. Okay, it's kept to, um, it cannot be reassigned. Okay, and so this means that if you end up binding a logic variable to one value, that value for the lifetime of that logic variable is always going to be the same. So if you use x plus x in any future expression within this unification framework, x is always going to be bound to 2. Okay, within the context of the Prolog program. Whereas with pattern matching, X plus Y could be any value over time just because of the lookup based on what you're using. You're just doing a simple comparison, binding it, and then returning it. Okay. You could technically make that as a single static assignment as well, but I think that changes the algorithm that Dr. Norbert provided. um, I'm not gonna kind of read through all of some of the reasons why it's useful to use unification. But briefly, I want to point out about the sophisticated reasoning because you could use unification to essentially do what we were talking about earlier with rules and figure out, given two equations, what the variables are if you're talking about unifying them, regardless of what them being different variables. Um, but uh, you need to understand that unification is not solving equations. It's not solving the constraints um, other than equality of particular logic variables or particular values. And the best example I think that's important for us to see here is if we have a function called unifier, all right, that we're going to be looking at in a minute. Um, and we have this expression that says, okay, and you'll see the logical inconsistency. A plus A equals 2, okay? And you are unifying that with the equation x plus y equals y, okay? What this is telling us is we're going to end up getting y bound to 2, and then since x plus y equals y, then 2 is bound to a, and then we get 2 plus 2 equals 2, which is clearly false. All right. So you can see that what this is showing us is the operators that are inside a particular equation mean nothing to the unification algorithm. It's just an uninterpreted piece of a sentence that we're actually looking into. Okay. Um, are there questions about this structure and why this is this way? Okay. Um, so let's pull up the actual code for this. All right. Okay. First, let me load this into my um, Lisp. Ooh, okay. 1 second. Looks like I have to rebind. Okay. 1 second. I have to do this again. I have to come here. Okay. Other locations. This. Okay. And this. Okay. Got it. So let me just load this up here again. What? Hold on. Oh, right, right. I think I named it differently. It was just PAIP. That's right. Okay, this code. Okay, PAIP is not found. Okay, hold on. Let me try this one more time. There we go. I had to reboot my Lisp in order for it to um, to uh, uh, in order to actually load this into my REPL. All right, so um, let's go ahead and pull up Roswell local projects, PIP Lisp, not local projects, PIP-Lisp. Okay, Lisp Prolog. I think this is a simple one that we're going to be looking at in a minute. Believe this is only dealing with, okay. So this is going to have a lot of stuff that we're not going to be covering specifically today, but we're going to be covering only the unification piece. In the next time we'll cover 11.3, which is going to include the uh, what's it uh, the automatic backtracking pieces. But once you understand at least some of the basic ideas of this, we may not even cover all of this stuff today, just because there's some stuff about this that I'm still kind of wrapping my own head on. So then I can give you guys some findings on. Um, to first discuss this, we're going to have to go back to what our match uh, variable code looked like in chapter 6. Yeah, from chapter 6. Um, that guy, if you recall, PIP-Lisp, Lisp, pat match. Okay, looked like the following. Okay, we had a variable symbol, and our pattern matching was basically a conditional statement that just checked whether or not we were matching particular variables. All right. Remember that there were also the default failure mechanisms we had no bindings to as well, so that we created constants on. But the idea is fairly simple. We just kind of used the extend bindings and match variable inside this pat match function to actually go in and use sublist to actually go and replace the bindings that we found for a particular input to the actual uh, the actual wildcard variable that's inside of the input before returning that information. Okay, so this here structurally represents also what we could do in unification, but with some caveats, which I'm still kind of working through. So let me just first show you the unified variable, unified code that we're going to be kind of discussing this time and next time. But to first begin with, we're going to first talk about the macro that's available here. Okay, the macro is a pretty simple macro. It's to add a fact, it takes the rest clauses, okay, as you can see here, and each clause is going to be thrown into a database. That database of predicates on line 20 is going to be effectively all the facts that are going to be, or predicates that are going to be stored in our database, and we're going to use a lookup in them when we do unification. Okay, and unification is separate from taking a Prolog program and interpreting it as part of the search procedure. All right. Um, add clause, all this does is it just simply has the name indicates, takes a predicate and throws it into the global variable, the special variable um, uh, DB predicates. Okay. Um, this is not doing, as far as I know, the unification piece just yet. Okay. Unify is its own separate um, function. Okay, so let's go and look at unify. Okay, unify. Unify actually leverages, actually it looks pretty simple when looking at it in the context of pattern match. So this guy is pattern match on the right hand side, and we have unify on the left hand side. And we could see that it looks roughly the same, right? We are first the default condition, if the bindings go to the failure condition, then that means we kind of given up on unifying the two expressions. If they're both equal, we'll just go ahead and then return all the bindings that we bounded. Otherwise, we check if the first x is a variable, and if it is, we'll unify the variable x in y and then add it to the set of bindings. All right. Um, if it's if y is the variable though, then we do the reverse. Okay. Um, otherwise, um, if they're both cons pairs, then what you end up doing is you end up uh, iterating through each variable one at a time, and you unify them within the context of the uh, the three cases that we just talked about. So essentially, going back to our example here, um, sorry, B B B. I need to go to slide scratch. There we go. If we take, for example, this one here, okay, what unify variable is going to go through is it checks to see what predicate we start with, all right? And if x is a variable, all right, so first actually what it does is it'll say, okay, um, this is a cons, this is a cons, all right. It's going to take Kim in this case, let's say Kim's for the simplest sake of example, and let's say that there's a bunch of facts already inside of our database that is related to Kim liking people, all right? We check to see if Kim's a variable. It's not a variable, all right? But we'll see X is a variable in this case, which is the second line 16. So what we'll do is we'll end up binding X, or at least try to unify the variable X with has the statement that we provided, Kim and comma X, and then we go through and we then bind the value that we ever come up with by looking up the binding, and then once we look up the binding, we'll just bind it to that logic variable and then return it. And what we're doing is this variable setup is going to then accumulate inside bindings and then we return it. Okay, and that's through the call extend bindings. This is where I kind of started getting a little confused, mainly because there's this piece called a curse check here that I did not get a chance to really delve into, and I'm still kind of working through that. So hopefully we can delve into it together. By the way, as we are looking at this code, if folks have any questions, feel free to drop a comment in the chat, and I will answer it as soon as I see them. Um, So let's go and talk about um, the reason why this unified variable is important is because, let's see. So we know that unified is identical to pattern matching because of the additional variable, additional case that they've written, the reverse. Um, if get binding var bindings, we then look up the bindings and then we extend it by adding the variable into the bindings. So let's look up here the this code. What is extend bindings first doing? I think is important to know. So interesting. Oh, extend bindings is from pattern matching. So this is in not in here. In here, extend bindings is doing what we did before. It's the sublisting, isn't it? Hmm. Where is extend bindings coming from? Get binding requires PAIP match. I have PAIP match available. Oh, is that in the utils? Let me just check something here. I'm just pulling up the equation, other, um, the other pieces of the program, so we can actually do a code review of all of it together. Okay. Lisp graph. Um, it's auxiliary functions. Okay. Go up here, split again, and let's add it in here. Here, Roswell local projects, PAIP Lisp. Let's do logs function. There we go. Yes. All right. Get bindings. So we know get bindings is just looking up a particular thing inside of because it's an associative list. The binding is an associative list. We're just getting the binding associated with a particular variable. And extend bindings, which is written here in line 30, what this is doing is it's just literally add a dotted pair here, extend bindings to the actual list. Okay. So what this function is doing is we're first grabbing, if we have an existing binding, then we do a lookup, and what the lookup is doing is literally a depth, it's not a depth first search, but it's just doing it's just trying to do an associative lookup that we just saw with the association. But then we're trying to grab, because a binding is a dotted pair, we're trying to grab the value of the dotted pair. All right, and that's the catter of the dotted pair that we retrieved. All right. So binding val, if you recall, is nothing more than a quick catter of the butter. All right. although they're just giving you the cdr just because you will see the list of with one value. Um, so what does this occurs check do? The occurs check is basically um, then so as it stands, this is solving multiple test cases related to unification, but the simple one, there's a way of just doing the simple test cases with like if that we're not even covering here. Um, if you just, but the thing is if you add it, there's a couple of cases where Norfolk explicitly talks about how just doing an if else with the get bindings that if you check to see if it exists, is that you're actually not handling all the cases um, just because of there are some pathological logic variables cases that if you attempt to unify them, it will end up overflowing in the stack and then you'll end up getting a trap. So it's not necessarily a good thing to check out. But if you're curious, the book actually does give you a simple version for you to play around with the simplest case before working your way up through this particular piece of code. So this is calling, yeah, It pushed up the problem, that's all right. Okay, so why is that this is right, right. Okay, so what occurs check does is nothing more than checks to see if a particular for a given equation or statement does variable occur anywhere inside of it. If it does, then it ends up leveraging um, it returns a failure in this case. Okay, so if we're doing an occurs check and we say occurs check, if the variable does exist within the particular expression that we're looking for, then we fail. Otherwise, what we'll end up doing is we end up doing the lookups in both um, either the direct binding that we see here in line 24, and we get the actual binding itself, or in the case of line 26, when we see that x is a actual logic variable that's associated with a particular binding, we then use um, the unification metric to actually go do the unify call to actually go do the unification between that lookup and the rest of its bindings before we actually go and extend it. Okay, so this is kind of the basic idea of what the unification algorithm does. Okay, but what it does at its heart is doing nothing more than taking a variable, a logic variable, taking the expression to actually do the lookup in for the logic variable, and then based on that expression, it tries to bind that logic variable to a value that's in the expression x, and extending that dotted pair, or using that dotted pair and extending the set of bindings that we've found so far before returning them all as part of the result of Unify itself. Okay. I encourage others to go and look at this code because this is a specifically it's recursive and it looks a little bit more confusing, but it's a lot simpler than it looks. You're just doing nothing more than resolving what we currently did with pattern matching to a generalized case where you're looking in both sides of the expressions to see if they pattern match. All right. In order and then taking the two sides missing variables, which are represented as logic variables, and binding them to the value of the equation of the other side. Okay. Um, with that, I think I'm going to have to end here because it is Uh, I haven't had a chance to actually go through some of the other examples with the programming language, specifically with Prolog. Um, but next time, what we'll do is we'll use this framework to actually learn Prolog programming. And this is important because as we start going through the Prolog implementation and we start talking about this last section, which is automatic backtracking, without knowing Prolog programming, backtracking won't make sense. Um, so we need to first learn Prolog programming to actually go and then understand why backtracking is important for Prolog programs. With the time remaining, I'm opening up the floor to questions. Any questions, Common Lisp related or the book related, feel free to ask them, and I'll try to answer them accordingly. Okay, well, in that case, I hope all of you enjoyed today's initial discussion on Prolog. This is going to be ongoing for the next couple of weeks. If you have any other topic ideas that you would like me to cover, feel free to drop me a line either in the YouTube comments or send me a message on Slack or Discord, and I will cover it. And with that, I hope you guys all enjoy your Monday evening, and I hope you have a good one. Thanks.